Problem number 18. Uncertainty in the time for a car to complete a race. The car begins with an initial speed v0 and maintains a constant acceleration a throughout the race. Both v0 and a have independent uncertainties of 10%. Which contributes greater uncertainty to your estimate of the time for a car to complete the race? Solution for problem number 18. If we have initial velocity, acceleration and full distance, we can find the total time using quadratic equation. At squared plus 2v0t minus 2d equals 0. The positive root for this equation is this one. Let's estimate this solution for small distance and for big distance. For small distance we have this approximation, which is about d over v0. And we can see that for small distance, time has dependent only from distance. It means that the main contribution was from uncertainty of distance. For big distance we have another estimation, which is this one. We see that this time mostly depends from acceleration, and we have only contribution for uncertainty for acceleration. It means that correct answer is A. And this was a solution for problem number 19. Problem number 19. A physical pendulum consists of a mass on one end of a massless rigid rod that can pivot about the opposite end, assuming the oscillations have an amplitude of 90 degrees. Which of the following graphs best shows the total acceleration of the mass as a function of the angular position theta measured between the pendulum and the vertical direction? Solution for problem number 19. Let's count what is the acceleration in any point with the angle theta to vertical. The acceleration could be split by tangential and normal acceleration. Tangential equal g sine theta, and normal could be found from energy conservation, because normal acceleration equal v square over L, where L is length of pendulum and v is the speed, and v square equal 2gl multiplied by 1 minus cosine theta. So we have normal acceleration equal 2g multiplied by 1 minus cosine theta. And now we can count what is total acceleration. The total acceleration square equal tangential acceleration square plus normal acceleration square, which is g square multiplied by 1 plus 3 cosine square theta. Now let's analyze this expression. In highest point where theta equal 90 degrees, cosine equals 0, and means that acceleration equal g, which could be for graph A, for graph B, and for graph E. For angle 0 degrees, cosine equal 1, and the acceleration equal 2g, which is 20. And we have only graph A, which is corresponding to this behavior, and also graph A corresponding to function which is decreasing from 0 to 90 degrees, which is a function we wrote here. So it means that correct answer is A, and that was a solution for problem number 19. Problem number 20. A block on a ramp is given an initial velocity v0 upward along the ramp. It slides upward for a time tu, traveling some distance and then slides down for a time td until it returns to its original position. What is a td in terms of tu? The height of the incline is 0.6 times its length, and the coefficient of kinetic friction between the block and the incline is 0.5. Solution for problem number 20. Let's write equation for distance as a function of acceleration and time. That's equal to 1/2 acceleration up multiplied by time up squared, which is the same as 1/2 acceleration down multiplied by time down square. And from this relation we can find that relation between times equal to opposite relation from square root of accelerations. Let's count accelerations up and down. Acceleration up equal g sine theta plus mu g cosine theta. Acceleration down equal g sine theta minus mu g cosine theta. So it means that time down over time up equal square root from acceleration up over acceleration down, and after putting all numbers we have square root from 5, which is answer C. That was a solution for problem number 20.